Okay, next two sections, 12.9 and 12.10, are, you can think of these as details, but they're necessary details because a lot of times the data that we get are going to be messy. So here's a summary of the sorts of problems that you might encounter with your data and trying to fit a regression line. So in section 12.9 we'll talk about unusual observations, and these are unusual residuals, and another term for these is outliers. Now the textbook reserves outliers for the first entry in section 12.10, but I consider these unusual observations as potentially outlying observations. And then there are things called high leverage observations. And in section 12.10, we'll talk about other types of outliers, what's known as ill-conditioned data. Spurious correlation is included in that list, but we will save that for, mostly that for chapter 14. I guess I will mention it in this lecture. And then there's problems with incorrect functional form and other types of model misspecification. So an unusual residual is when there is an individual y value, a dependent variable, that is very poorly predicted. I should put very poorly predicted by the regression model. Okay, so using the empirical rule, any standardized residual greater than 2 is unusual. And the standardized residuals are the raw residual, the raw error term divided by the standard error of the error terms, which is what we talked about when we in the previous section. Okay, and then any standardized residual greater than 3 is, I should say, potentially an outlier. Okay, and then what to do, we'll talk about that when we get to outliers. The high leverage problem might arise if you have an observation that have x values for the independent variable that are far from the mean of x. So here's a little picture down here in these highlighted data points. The mean of x is at this dotted line, and the potentially high leverage data points are way on the outside, like you're sitting on a seesaw. Okay, so these can have a big effect on the slope of the line, especially if they are if they have a relatively large error term. Okay, so to find leverage, you can use a leverage statistic, and this is automatic in software like SPSS, but in Microsoft Excel you have to construct it. But the leverage statistic is equal to 1 divided by the sample size plus the square deviation from the mean for each individual observation, and then that's divided by the sum of the square deviations for all of the x's. Okay, and in this case, when the x value, the dependent variable, is right at the mean, the leverage statistic is equal to 1 over n. So one rule of thumb is that if the leverage statistic is 4 times greater than the sample size, or is 4 times greater than the leverage statistic at the mean, then the variable is potentially influential. Okay, and if you have observations like that in your data, you can consider treating the high leverage observation as an outlier. Okay, and then our last section of this chapter is other regression problems or other regression issues. So in addition to unusual observations, you can have outliers that are that arise for a bunch of reasons. You can have just some bizarre data in there, or some impossible numbers, like if you have salary data and one of the numbers in there is 5 million, and you know you know that no one has paid $5 million at your company, you might think that that is an outlier. It might result from a coding error. Someone may have tapped in a couple extra zeros. One thing that you can do is you can discard those observations and re-estimate your model. You don't want to discard them permanently, but discard them temporarily and re-estimate the model. Or you could top code these observations. So when you top code data, you might have, imagine you've sorted your observations, and these are the 5 highest values for X, and you've got a value here that's 1,000. And you think that that might be a result of a key punch error, but you think that it's still a high value. So top coding would replace this odd number with a number that you think is more reasonable, but it's still high. So you might replace it with the highest value. So there's 2 things that you can do with outliers: discard the observation wholly, or top code it, or bottom code it if it's too low, if you think it's too low. And that's combined, that's 2 ways of cleaning your data. And most all raw data sets require cleaning. Okay, when you're doing your analysis, you need to be careful about conducting more than one round of cleaning. With a data set, you're always going to have a chance of having an outlier, unusual observation, after each round of cleaning. So if you continue to clean your data each time, then you're going to wind up with basically an artificial data set. Okay, and then if you do clean your data, always report your cleaning efforts. Just describe what you've done, just so the reader knows what your data really looks like. Okay, ill-conditioned data is a situation that you can encounter, but we probably will not encounter it this semester other than a question on the quiz or the final. Well-conditioned data is when the data values are of the same order of magnitude. For example, if you're estimating income and that's in the thousands, and years of education is in the tens, like 12 for a high school graduate, 16 for a college graduate, sometimes those 2 different magnitudes can cause a problem. So you can fix that by dividing income by 1,000, and then your incomes are numbers like what we see here, 57 and 48 and 41 and 38, and your education values are in the tens. Okay, spurious correlation. Remember, we talked about regression models don't prove causality. Okay, you're basically measuring correlation. We might need some theory or some other aspect of the underlying relationship to suggest causation, but you can have correlation between 2 variables that's for no reason at all, and that's known as spurious correlation. Okay, they can be related simply because of the way they're defined or measured, and also simply because of coincidence. Sometimes this can happen in cross-sectional data like we've talked about now, where the data values are measured at one point in time. It can happen more often in time series data, where you're looking at 2 data series over a certain time period. And we'll talk more about how that can happen in time series data when we get into chapter 14. Okay, so sometimes functional form might matter. So let's go all the way back to our discussion about correlation at the beginning of chapter 12. So functional form is when you specify your regression model as linear, like we do in these like we might have in these first 2 pictures on the left, but your data is actually nonlinear. Okay, so if we specify this nonlinear relation with a linear model, then we're going to end up with a poor regression model. So here's 3 alternative functional forms to the linear model. And I should just, maybe I should add the linear model to make this clear. So a linear model is y equals the intercept plus the slope times x. What's known as a semi-log model takes the natural log of y, and then the right-hand side is a linear model. A double log model, you take the natural log of both the independent variable y and the dependent variable y and the independent variable x. And this estimates both of these estimate a non-linear relation. And then once we get into chapter 13 and talk about multiple regression, you can think about a quadratic model where you add a squared term for the independent variable. A lot of times this might, different functional form might improve model fit. Your R-squared statistic will increase. It might reduce heteroscedasticity, and it might also improve the normality of the residuals. Okay, when you do consider a different functional form, you have to interpret the slopes differently. And so here's how the slope is interpreted for the semi-log model and the double log model. So with a linear model, the slope is just the slope. But with a semi-log model, the slope coefficient B1 is interpreted as the percentage change in y when the independent variable x changes by its units. Okay, in a double log model, the coefficients are elasticities. So the slope coefficient is interpreted as the percentage change in y divided by the percentage change in x. Okay, and then finally there's other ways that a model can be misspecified. Sometimes a relevant predictor has been omitted from the model. That's called omitted variable bias. And this is the problem that leads us into chapter 13. So you might know that you have omitted variable bias if there's an important variable, an important theoretical variable that's left out of the model. If the model has statistically significant but unexpected signs, like you're expecting a positive sign to the slope, but you actually get a negative sign, or if the model has a very poor fit, then you might know that there's an important variable that should be included. And when this happens, the estimated coefficients are biased and inconsistent. Okay, the worst problem with regression models is when your coefficients are biased. And the solution is to formulate a multiple regression model. So that leads us into chapter 13.